Welcome to another topic, compound cylinders. Here in this video we will be seeing introduction, why to use compound cylinders, demonstration of cases, stresses in compound cylinders and numerical problems. Let us see all of them. Let us see first what are compound cylinders. Now you can see two cylinders, one is of higher diameter, one is of lesser diameter. Now this higher diameter cylinder will be heated up. Then it will be expanded. Now the smaller cylinder will be inserted into this like this. Then they will join together and form a single unit. Now I said the outer cylinder will be expanded in order to insert the smaller cylinder. So outer cylinder is expanded, so it is subjected to tensile stresses. And inner cylinder is compressed by the outer cylinder, so it is subjected to compressive stresses. Of course the inner cylinder is also exerting some tensile forces on the outside cylinder. However, outer cylinder is subjected to tension, inner cylinder is subjected to compression. So why should we use compound cylinders? Now if you see this compound cylinder, there is a junction over here. That junction will reduce hoop stresses. So comparatively single thick cylinder, the compound cylinder will minimize the hoop stresses developed in the thick cylinders across the thickness. We shall see with the stress diagram. Outer cylinder is subjected to tension as I said, and inner cylinder is subjected to compression as it is compressed by the outer cylinder. Here you can see stresses due to fluid pressure, right? We have seen this with the example in the previous video. Please remember that. If you have not seen, please go and see that. And final stresses, so we have to combine these stresses and form a final stress diagram, which ultimately proves that there are stresses minimized. So I will prove that by the end of this video with an example. Let us move to demonstration of possible cases of fitting. So as a compound cylinder is combination of two cylinders, there are three possible cases. So here we can see four glasses. This is informal example. So we are seeing that first cylinder is a host of these three glasses. So I am telling the glass as a cylinder. So let consider these as cylinders. Okay. So now let us say first cylinder to fit into, second cylinder to fit into first one. So that is tight fit. So it is not going completely into that. So we can say that is worst case of tight fit. And secondly, we shall see this glass to be fitted into this. That is very perfectly fit, and we can say that is the ideal case, and that will not fall down. And we shall see another case of loose fit. So if you see that, that is very loose and it will fall down very easily. That is again worst case of loose fit, right? So special thanks to Kalyan Ram sir, professor of civil engineering, who has provided this video. Thank you very much sir. Let us get into stresses in compound cylinders. See here, let me take R1 as a inner radius of compound cylinder, R2 as the outer radius of compound cylinder, R star is the radius at the junction of two cylinders, right? We have three steps of derivation. First we have to see stresses in empty cylinder, stresses in outer cylinder and inner cylinder. In the secondly, we are inserting fluid into that. We are considering the compound cylinder as a single unit, and we are finding the stresses of the cylinder subjected to internal fluid pressure. And thirdly, we have to find out resultant stresses combining these two. So let us see first step, empty cylinder, stresses in outer cylinder. So let us find out what are the Lehm's equations we have. So if you remember, we have the Lehm's equations as Px is equal to b1 by x square minus a1. I am telling b1 a1, sigma x is equal to b1 by x square plus a1. Take them as equations 1 and 2. So I am taking b1 and a1 as constants of outer cylinder, and inner cylinder I will take a2 and b2. Okay, as of now let us see, let us apply boundary conditions. So what are boundary conditions? Let us see outer radius of outer cylinder. So outer boundary, that is at radius r2. So x is equal to r2, and what happens to px? Px will be 0. So let us substitute these two in equation 1. What will we get? In the place of px I will substitute 0, b1 by, in the place of x I will substitute r2 square minus a1. Take it as equation number 3, right? And another boundary is inner radius of outer cylinder. So at the inner, what is inner radius of outer cylinder? That is nothing but radius at this junction, r star. So x value will be r star here. And what happens to p? The p is pressure at the, px will be the pressure at the junction, p star. So let us substitute these two in equation 1 again. What will we get? In the place of px, I will substitute p star is equal to b, b1 by, in place of x I will substitute r star square minus a1. Take it as equation number 4. So by solving equations 3 and 4, you can get the values of a1 and b1, and you will get this hoop stress value variation in the outer cylinder by substituting a1 b and b1 here. a1 b1, and in place of x you have to substitute outer radius of outer cylinder, inner radius of inner cylinder. That's it. That is about stresses in outer cylinder. Let us move to stresses in inner cylinder. Again we have Lehm's equations. Px is equal to, so we have to take here b2 by x square minus a2, and sigma x is b2 by x square plus a2, and the equations are equation 5 and equation 6, right? So let us apply now again boundary conditions for inner cylinder. First boundary is outer radius of inner cylinder. So inner cylinder has outer radius, inner radius. So let us take outer radius first. I will substitute in place of x r star, and I will substitute in place of px p star. Right? Let us substitute in equation 5. What will we get? In place of px p star is equal to b2 by, in place of x r star square minus a2. Take it as equation number 7, and let us apply another boundary condition, that is inner radius of inner cylinder. What is the radius here? r1. So in place of x I will substitute r1, and in place of px I will substitute how much? 0, because the cylinder is empty, there is no fluid inside, there is no pressure, so it is 0. Let us substitute in equation 1 again. So in place of px I will substitute 0 is equal to b2 by, in place of x I will substitute r1 square minus a2. Take it as equation number 8. So if we solve equations 7 and 8, we will get the values of b2 and a2. By using these two values, you can find out the hoop stress variation in inner cylinder. If we see the problem, you will understand. So let us move to compound cylinder. Compound cylinder subjected to internal fluid pressure. Now we are considering this compound cylinder as a single unit, not two cylinders. It is a single unit having pressure inside, fluid inside. So let us see Lehm's equations we have. Px is equal to b by x square minus a. So I am taking capital letters here. Sigma x is equal to b by x square plus a. Take them as equation number 9, and this is equation number 10. Right? So and here a and b are constants of compound cylinder. So let us apply boundary conditions for this compound cylinder. What is the first boundary condition? Outer radius of compound cylinder. So outer radius means x value I am considering it as r2, outer radius r2. And what happens to px? 0, there is no pressure outside. So let us substitute these two in equation 9. What will we get here? In the place of px I will substitute 0 is equal to b by, in place of x I will substitute r2 square minus a. Take it as equation number 11. Right? Let us apply another boundary condition, that is at inner radius. So what is that? What happens to x at inner radius? r1. And what happens to px? That is fluid pressure, because now fluid is there inside, so we have to consider as fluid pressure. Now substitute again in equation 9. What will we get? In the place of px I will substitute p, that is equal to what is and b by what is x, r1 square minus a. So take it as equation number 12. Now by solving equations 11 and 12, we get the values of constants capital A and capital B. After using that, you can easily find out the hoop stress variation in compound cylinder. So that will be better understood by problem. Okay, let us see now resultant stresses. That is algebraic sum of hoop stresses caused by shrinking and those due to internal fluid pressure. Stresses when the fluid is when the cylinder is empty, and stresses when the compound cylinder is having internal fluid. So let us see a problem that you will better understand. A compound cylinder is made by shrinking a cylinder of external diameter 300 mm and internal diameter 250 mm, and another cylinder of external diameter 250 mm and internal diameter of 200 mm. This is on another cylinder. Okay, the radial pressure of at the junction after shrinking is 8 Newton per mm square. Find the final stresses set up across the section when the compound cylinder is subjected to an internal fluid pressure of 84.5 Newton per mm square. Let us see the solution first. Before that, let us write the data given. A compound cylinder is made by shrinking cylinder of external diameter. So external diameter is given. External. Can you tell me what is external radius outer radius R2? R2 will be this 300 by 2, external diameter by 2, that is 150 mm, internal diameter 250 mm. So internal diameter of outside cylinder is given. So with that you can find out R star. So R star will be 250 by 2. R star will be 250 by 2 because that is the diameter divided by 2, 125 mm. And if you see on another cylinder of external diameter 250 mm, so see here 250 outer diameter, inner radius and inner diameter outer radius are same, and you will get that is r star, radius at this junction, right? They should be same actually. And the internal diameter 200 mm, so r1 is equal to 200 mm, sorry, radius is 200 mm, so r1 will be 200 by 200 mm. That is the data given. And one more thing they have given to us, the radial pressure at the junction after shrinking is 8 Newton per mm square. So P star they have given to us as 8 Newton per mm square. Find the final stresses set up across the section when the compound cylinder is subjected to internal fluid pressure. So internal fluid pressure is given as 84.5 Newton per mm square. Again we have three steps solution here. That is, we have to find out stresses in empty cylinder, outer cylinder and inner cylinder. Later we have to find out stresses in compound cylinder with fluid pressure. Later we have to join them. Later we have to use them in order to find out resultant stresses. Let us see step by step. First step, we are calculating stresses in empty cylinder. First, outer cylinder. Again we have Lehm's equations. Px is equal to b1 by x square minus a1. Take it as equation number 1. And sigma x is equal to b1 by x square plus a2. Take it as equation number 2. Let us now apply boundary conditions. So boundary conditions for outer cylinder, as same procedure what we have derived should be followed here. At outer radius of outer cylinder, outer radius means, so x value will be r2, r2, that is how much, 150 mm. And what is px, will be 0, there is no pressure outside, right? Let us substitute these two in equation 1. What will we get? So 0 in the place of px is equal to b1 by x 150 mm 150 square minus a1. Okay, take it as equation number 3. Let us apply another boundary condition at inner radius of outer cylinder. Outer cylinder having the boundaries are its inner radius, its outer radius. So we are saying for inner radius of outer cylinder. So that will be how much? X will be r star and p will be p star. Let us substitute them in equation 1. What will we get? So here in place of px I will substitute p star, that is equal to b1 by, in place of x I will substitute r star square minus 1 a1. Take it as equation number 4. Right? What is r star here? 125 square minus a1. That is equation number 4. So now from equation 3 I can write a1 is equal to b1 by 150 square. Now this value will be substituted here and the p star is 8. Okay, as given in the question. Now only unknown value is here b1. You can easily find it out. The entire simplification calculation is there in the notes. Please download it and see. Description in the notes. Notes will be available at the description of the video. Please click the link and download the notes. Okay. However, you will get the values of b1 as 4090 90.9, and we got the value of A1 as 18.18. So with these values you can find out this hoop stress. Now I will write hoop stress as B1 by x square plus A2, sorry A1, sorry, this is A1, and B1 we have 4090 90.9 by x square plus 18.18. Now I will find out at outer radius of outer cylinder, that means at 150 mm. So sigma 150 will be 4090 90.9, by in place of x I'll substitute 150 square plus 18.18. So upon calculation you will get the value as 36.36 Newton per mm square, right? So in the second case we have to find out another boundary. For this sigma, how much? The inner radius of outer cylinder, that is 125 mm. So again 409090.9, by in place of x I'll substitute 125 square plus 18.18. So however, how much? After calculation you will get 44.36 Newton per mm square, right? Let us calculate, that is for outer cylinder. Stresses in outer cylinder. Let us see for inner cylinder now. This is B, step B, inner cylinder. So we have the Lenz's equations as Px is equal to B2 by x square minus A2, and sigma x is equal to B2 by x square plus A2. And these are equation number 5 and equation number 6. Let us apply now boundary conditions. Outer radius of inner cylinder. At outer radius what will happen? So x value will be r star, that is a junction, that is how much? 125 mm. And what happens to p? X, that will be p star, that is radius at, stress at the junction. So that is pressure at the junction, that is 8 Newton per mm square. Let us substitute these two in equation 5. What will we get? So in the place of px I will substitute 8 is equal to b2 is b2 and x is 125 square minus a2, right? Take it as equation number 7. So that is outer radius. Now let us calculate inner radius. At inner radius what happens to x? R1. Radius is R1 and px will be 0 because there is no fluid inside. This is the empty cylinder. The R1 is how much? 100 mm. Let us substitute these two in equation 5 again. What will you get? In the place of px 0 is equal to b2 by in place of x 100 square minus a2. So I will write it as a2 is equal to b2 by 100 square. If you substitute this a2 value here in equation 7, you will get the b2 value. Subsequently you can find out a2 value. So ultimately if you solve equations 7 and 8, you will get the value of the equation. The solution is very clearly given in notes. So now you get the values of a1 and b1 as b1 is minus 222222.22, and b2, right? B2 a2 is minus 22.22. These are the values you get. And let us see for sigma. Let us substitute in equation 6. Sigma x is equal to, we have sigma x is equal to b2 by x square plus a2. So what is b2? So minus 22.2, sorry, 22.22 by x square minus 22.22, that is a2 value here, sigma x. Now we have to find out for outer and inner radius of inner cylinder. So sigma for inner radius we have 100, radius 100. So in place of x I have to substitute 100. 2222 by 100 square minus 22.22. So the value we get it as minus 44.44 Newton per mm square. And its outer radius, how much? R star, that is 125 mm. So sigma at 125 will be again same, minus 22.22 by, in the place of x I'll substitute 125. 125 square minus 22.2. So ultimately we'll get the value as minus 36.44 Newton per mm square. Right, these are for inner cylinder when it is empty. Let us find out the stresses in compound cylinder subjected to internal fluid pressure. We have the Lehm's equations as Px is equal to B by x square minus A, and sigma x is equal to B by x square plus A. I am taking capital values here. Take it as equation number 9. This is equation number 10. And A, capital A and B are constants of compound cylinder. Let us apply boundary conditions again. At outer radius of compound cylinder, that means at R2. So R2 will be how much? So X will be R2, that is 150 mm. And what happens to pressure outside? Px will be 0. Let us substitute in equation 9. What will we get? In place of Px, I will substitute 0 is equal to B by, in place of X, I will substitute 150 square minus A. Take it as equation number 11. And let us see another boundary condition at inner radius of compound cylinder, that means at R1. R1, what will happen? So X will be at R1, that is 100 mm. And what happens to Px? That is P. Now internal fluid pressure is there. Right? Let us substitute these two in equation 9 again. So in place of Px, I will substitute P is equal to B by, in place of X, I will substitute 100 square minus E. Take it as equation number 12. So that P was given as 84.5 in question. So 84.5 is equal to B by 100 square minus A. That is actually equation number 12. So if you solve equations 11 and 12, you will get the values of A and B. So let us see what are the equations here. Constants here. B value we get it as 1521000, and A value we get it as 67.6. Now use them in equation 10. Sigma x is equal to B by x square plus A. So in place of B, I'll substitute 1521000 by x square plus 67.6. So now let us see at all points compound cylinder is sigma x at 100. Hoop stress at inner radius 100, that is 1521000 by 100 square plus 67.6. So how much? So we will get it as 219.7 Newton per mm square. And let us find out sigma 125. At junction also we shall find out. So that will be 1521000 by 100 square plus 125 square plus 67.6. So what will we get now? 164.94 Newton per mm square. And sigma at outer radius R2, how much? 150. So that will be equal to 1521000. In place of x, I will substitute 150 square is plus 67.6. Ultimately the value you will get it as 135.2 Newton per mm square. That is all about compound cylinder. We have to find out resultant stresses now. As the definition, resultant stresses are algebraic sum of the hoop stresses due to shrinkage and due to internal fluid pressure. So till now we have these values. So inner cylinder shrinkage, all these values we got it here, and this is for outer cylinder, we got it here, and compound cylinder, these are the values. See here at radius 100. So let us join due to shrinkage, due to fluid pressure. We have two values. Those are first one plus sigma 100. This is due to fluid pressure, fifth one. That is minus 44.44 plus 219.7. So how much that is? 175.26. So these minus values indicate that is compressive stress. So previously if I have not mentioned that, please understand, where negative sign indicates compressive stress. At radius 125 mm. So where is 125? Here 125 is there due to shrinkage minus 36.44, and another we are talking about inner cylinder, right? So we don't consider outer cylinder here. So inner cylinder due to shrinkage 125, and due to fluid pressure this is plus 164.94. That is how much? 128.72. This is also positive. This is tensile. This is also tensile, right? At the radius, outer cylinder radius, uh, 125 mm. So we have to take this. So 125 mm due to shrinkage, due to fluid pressure. Let us add them. So this is 44.36, and this 125, this is how much? 125, this is 164.94. So you'll get it as 209.3 Newton per mm square. And at radius 150 mm, at radius 150 mm for outer cylinder, this is 36.36, and for due to internal fluid pressure we have 135.2. So we'll get it as 171.56. And this stress diagram clearly represents this. And due to tension, for this outer cylinder, these are the values. Say this is 36.36, 36.36 here, and 44.36 here. And for inner cylinder we have minus 36.44 here at radius 125, this is junction, and here minus 44.44. And this is for fluid pressure. This is 135 here, 164 at the junction, 219 at the outer cylinder, sorry, 219 at the inner part. And if we join them, so we get the resultant stresses as this is for inner cylinder. This is for inner cylinder, how much? 175.26 is this, and at 125 this is 128.92, and this is again 209.3 here, outer cylinder starting, and this is at the end 171.56. So if you compare these stresses, the resultant stresses obtained are less than the only the compound cylinder due to fluid pressure. If we don't take compound cylinder, we'll finalize these values. If you take compound cylinders, we have to get the resultant stresses due to shrinkage, right? I hope you have understood. If you get any doubts, please contact me. And we have a practice problem. If you do it, you will understand it better. If you get any doubts during solution of this problem, please let me know. I'm very happy to solve your doubts. Please do this problem and send it to my mail. Thanks for watching. Once again, a special thanks to Dr. Kalyan Ram sir for providing input to my video. Thank you.